We're going to solve a couple of systems of equations and just talk about our results, okay? And then a little bit of commentary to follow. But we say, consider the following systems of equations. We want to solve the system using any method we would like and explain how we know our answer is right. Also, the significance of the solution points, okay? So when we look at this here, we say we have two equations, two variables. They're both linear and they're both in standard form. So one thing we can do is we can graph it. So for instance, in the first equation here, we say if we made like a, an intercept method here, we say make a t-chart. We say plug in 0 for x, we get 4 for y. Plug in 0 for y, we get 4 for x. So like if we wanted to sketch its solutions, we could say, well, then they would lie along this line right here. And so we could at least get a good idea of what its set of solutions looks like. So we say x plus y equals 4. Same thing for this equation here. I suppose we could, let me move this out of the way because I know I'm going to be doing some work here in a minute. But find the intercepts for the second equation. We say x and y. Plug in 0 for x, we get negative 2 for y. And plug in 0 for y, we get a positive 2 for x. So we say 2 zeros on the graph. And 0, negative 2 is also on this graph. So we'd say going up and over here, looks like we have a solution pair that is developed. But let me go ahead and finish drawing the rest of this in and label it. So we say x minus y equals 2. So the first thing I want to note here is this. We have a suspected solution pair. I think this is the point 3 comma 1. I'm going to put a question mark after it. But we say this right here is the solution. So in terms of the number of solutions, we say it has one solution. So we say one solution. Something new that I want to share in this video is essentially this. The fact that we had a solution is a pretty significant thing. So when we talk about a system that has a solution, okay, so we say, types of systems. I suppose we'll write this down. I want to make sure we have this down. Types of systems, we say any system that is consistent, okay, can follow in one of two ways. We can say it can be consistent independent, which is very common, independent, or consistent dependent, okay. We say a system can be this or it can be inconsistent. The fact that we got an answer in the first place indicates that this is a consistent, or what we call a consistent system. And the fact that we got one answer means this: we didn't get infinitely many answers. These graphs do not run into each other for always and ever, okay, at every point. So we say because they do not live together, we say it's independent. So we say at least one, but not infinitely many. And don't write infinitely many that way, write infinitely many with the word. I just ran out of space, okay? And we say this has infinitely many solutions. I'll even write it out here. Infinitely many. And we're going to run into systems that have this, okay? And then we say this is no intersection between the graphs down here. So we'd say inconsistent is no solution. So I'm putting parentheses inside parentheses on this one. We say no solutions. Okay, so we say that this is a consistent system. I just want to go ahead and label this now because we're going to get in the habit of doing this. Consistent, and it's independent because I didn't get infinitely many solutions. So that's true about this. So now, solving this algebraically, you notice we could have done elimination very easily here. We say those would have canceled out. We would have gotten 2x equals 2 plus 4 is 6, and we say x equals 3. You could see that I get my 3 here. And then plugging this back into the first equation, we say x plus y equals 4. If I plug this in for x, we say blank plus y equals 4. If I plug in a 3 right here, one can easily see that y comes out to be 1. So we'd say the point 3 comma 1 is definitely the solution pair, and it occurred right here on our graphs. Okay, so example number 4, actually, we could start with the graph here. We'd say negative x plus 2y equals 4. Let's go ahead and find our intercept on this one. 0 for x, what do we get for y? 0 for x, what do we get for y? We say 0 for x, we get 2y equals 4, so this is 2. Plug in 0 for y, we get negative x equals positive 4, so negative 4 is 0. So we're going to go ahead and graph this out. We say negative 4 comma 0 is here, 0, 2. So we have our set of solutions to this first equation is this guy right here. We're going to label this. We say negative x plus 2y equals 4. And then last but not least, we say looking at this one here, we say if I found x and y intercepts for the second equation, plug in 0 for x, plug in 0 for y. 0 for x gives us a y value of a positive 2. And plugging in 0 for y gives us an x value of negative 4. So you notice here I plug in, say negative 4, 0 is right here, we say 0, 2. So this is actually the equation 2x minus 4y equals negative 8. The interesting thing here is that they're exactly the same. So what this means is, how many times do they run into each other? How many common solution pairs do they have? How many points of intersection do these two lines that we have? We say infinitely many. Infinitely many. Furthermore, we could classify this system as being consistent because, hey, you know what? We got at least an answer, and it's consistent dependent. Okay, so we'd say this was an example of a consistent dependent system. The last system I want to draw out here really quickly is this one. I would say, what if I had like a line and a parabola? But we'd say this would be an example of an inconsistent system, just to put this into context. But yeah, we were able to solve these using any method we liked. We used convenient ones. Cheers. Amend to this video, and that's essentially this, and I wanted to solve this system algebraically as well. So we have negative x plus 2y equals 4 and 2x minus 4y equals negative 8. One thing I want to say about this is they graph the same set of solutions, so which means they must be the same line. They have to have the same equation. We just couldn't really see this here. So if we solve this by, say, elimination method, we would have taken the top equation, say, times 2 to eliminate my x's, say. We would have gotten this, and I'll transplant my system down here. We say negative 2x plus 4y is equal to 4, and we would have had still the second equation, 2x minus 4y, so minus 4y is equal to negative 8. And adding these together, you can see that the whole left side cancels out and the whole right side, actually this should be an 8 up here. The whole right side cancels out and I get this. So whenever you have two equations that cancel out perfectly, this is a good indication that you have a consistent dependent system and that it has infinitely many solutions. Inconsistent systems give you statements like this. We say 0 equals 7, or this is a false statement, or